Hello and welcome. This video is focusing on SLO 15 and 16. So we're going to determine the number of different oblique triangles that exist given certain side lengths and angle measures. And we're also going to use the law of sines and the law of cosines to solve oblique triangles, where we will determine all missing side lengths and angle measures. To solve an oblique triangle, meaning to find all missing side lengths and angle measures, the law of sines or the law of cosines must be used. An oblique triangle is a triangle at a 90-degree angle. The law of sines and the law of cosines can be used to find both missing sides and missing angles. We're first going to focus on the law of sines. There are three types of triangles that you would use the law of sines for to find any missing side lengths or angles. We're going to start by talking about the ASA triangle, or the angle-side angle triangle. This is when there are two included angles which sandwich one included side length. So angle, the side, the angle. Another triangle we would use the law of sines for is an AAS triangle, or an angle-side angle triangle. This is when there are two included angles and one side length next to an angle. Angle, angle, side. Then there's the side-side angle triangle, or the SSA triangle. This is when there are two included side lengths and one included angle next to the side. So side, side, angle. Let's now focus on the actual formula for law of sines. So let's focus on the actual formula of the law of sines. So this formula states that the sine of angle A over side A is equal to the sine of angle B over sine B, which is equal to the sine of angle C over side C. Why is this the case? Well, let's look at it. If we draw an altitude down, we can form two right triangles. This will help to explain why the law of sines is like this. So let's focus first on angle A. Well, if we were to find the sine of angle A, we would have h over c. We manipulate this to get the value of h, which would be c sine A. Let's do the same for angle C. The sine of angle C would be h over A, meaning h would be equal to a sine C. These two are both equal to h, meaning they can be equal to each other. So let's put c sine of A to equal a sine C. Well, to get rid of the a's and c's from both sides, we can multiply both by 1 over ac. This would mean that it simplifies to the sine of angle A over side length A is equal to the sine of angle C over side length C. This can be represented with the other angles in a triangle as well, which explains why the law of sines is this way. Let's put the law of sines to use. We are asked to find the length of side D. Based on the law of sines, each angle corresponds to its side, and we're given an angle-side angle triangle here. So what we can do is we can put sine of 75 degrees over D, because we know we're looking for the side length D, and we can put the sine of E over 30. Now we first have to find the angle E value. So we can do this by remembering that a triangle adds up to 180 degrees. So we're going to add our given angles, 75 degrees and 45 degrees, which will equal 120 degrees. Subtract that from 180 degrees, and we have 60 degrees equals E. We'll plug this into the equation. So now we have sine of 60 degrees over 30 degrees and sine of 75 degrees over D. If we cross multiply, we'll have D sine 60 degrees equals 30 sine 75 degrees. So now that we have cross multiplied, we have it written as D sine 60 degrees equals 30 sine 75 degrees. So sine of 60 degrees is a special angle. This means that d times root 3 over 2 can now be the way this is written. And the sine of 75 degrees is not a special angle. However, you can easily find the value by putting sine of 75 degrees into a calculator and make sure it's on degrees mode in order to find this. So when we do that, we have root 6 plus root 2 over 4, and we're still multiplying that by 30. So when we multiply this by 30, we get 15 root 6 plus 15 root 2 over 2, and this is still d times the root 3 over 2. To isolate d, because we're finding side length d, we'll divide both sides by root 3 over 2. And this simplifies it down to d equals 15 root 6 plus 15 root 2 over root 3. And if we simplify that even further, we get 5 root 6 plus 15 root 2. So this is the length of side D in its exact value. You could find its decimal form, but we're not doing that in this case. Let's look at another example. We are now looking at an angle side triangle, or an AAS triangle. We know this because we have an angle, and a side. We are asked to find the length of side H. Again, we're using the law of sines, meaning we'll need to find the corresponding angle. We'll do this by doing 180 degrees equals 30 degrees plus 105 degrees plus h degrees. And then we'll have 180 degrees equals 135 degrees plus h. We'll subtract 135 from both sides, giving us 45 degrees is equal to h. We can now set the law of sines up. So we'll have sine of 45 degrees over h, since we're looking for h, is equal to the sine of 30 degrees over 22, because that's one of our given side lengths. We'll cross multiply once again to get h sine 30 degrees and 22 sine 45 degrees. As we know, the sine of 30 degrees is on the unit circle, as well as the sine of 45 degrees. So we can substitute those in. We'll have h of 1/2 equals 22 times root 2 over 2. If we simplify this, we'll just have h times 1/2 equals 11 times root 2. We'll divide 1/2 by both sides to isolate h, and this gets us h equals 22 root 2 as its side length. Again, we could find a decimal, but it's really not necessary in this case. This will be the end of part 1 for SLOs 15 and 16. Come back to the next videos where I will be discussing an SSA triangle and how that works, as well as the law of cosines. Thanks for watching.